Continuing on physical chemistry, chapter 4, we're beginning section 8 now. So now we're going to derive the condition for phase equilibrium. So let's say that we have silver chloride solid in equilibrium with silver chloride aqueous. So here's our test tube. We have two phases. We'll call one delta and one beta. So at the bottom we have the solid silver chloride, and then up here we have the aqueous solution with the silver plus ions and the Cl minus ions. Now let's say we put some silver chloride solid in the water. It's gonna, well, if the solution is already saturated, it's gonna dissolve. So the differential of the number of moles of substance J is going to be positive. Now remember, we showed before the sum over all the phases and the sum over all the substances of the chemical potential I, substance I in phase alpha, times the differential of the number of moles of substance I in phase alpha is equal to 0. So we have the chemical potential of substance I. Was that supposed to be an I or a J? Okay, so anyway, yeah, we're using J now. So the chemical potential of substance J in phase beta times the differential of the amount. Wait, should that be Ni? dNi? Holy cow! Got a typo here. All right, so mu J phase beta, that should be dNj phase beta, plus the chemical potential of substance J in phase delta times the differential of the number of moles of substance J in phase delta is equal to 0. Wow. Anyway, so we have minus the number of moles of substance J in beta is equal to the number of moles, the differential of the number of moles of substance J in phase delta. In other words, this conservation of matter. If you have a certain amount of matter going from phase to phase, however much disappears from here has to reappear there, or vice versa. So that means also the differential in the number of moles of substance J in phase beta is equal to minus the differential in the number of moles of substance J in phase delta. Like I said, that's just conservation of matter. That's basic physics there. So here we have minus mu sub J in phase beta times the differential of number of moles of substance J in phase delta plus the chemical potential of substance J in phase delta plus the differential of the number of moles of substance J in phase delta is equal to 0. So see what we did there? We substituted in. We said those two were the same, so we substituted in. We brought the minus sign down. So now we can factor that out, and we can say the differential of the number of moles of substance J in phase delta is equal to the difference between the chemical potential of the substance J in phase delta minus the chemical potential of substance J in phase beta. That's still equal to 0. Now, we're not at equilibrium yet, so that we're going to say the number of moles moving is not 0. So we're going to say the differential of the number of moles of substance J in phase delta, it can't be 0. Therefore, this other term must be equal to 0. So we're going to say the chemical potential of substance J in phase delta minus the chemical potential of substance J in phase beta is going to be equal to 0. So just moving those to opposite sides then, we're going to say the chemical potential of substance J in phase delta is equal to the chemical potential of substance J in phase beta. That is our condition for phase equilibrium. Now this is assuming pressure volume work only and that we're in constant temperature and pressure. Now let's talk, and this, of course, we're at thermal and mechanical equilibrium. Now the chemical potential of the same substances, so what this tells us, the chemical potential of any substance, the same substance, in different phases is going to be equal at equilibrium. For a system that's not at phase equilibrium, though, we have the differential of the Gibbs free energy is going to be less than 0. This is when we're not at material equilibrium. So we're going to have the sum over all the phases alpha and the sum over all the substances I of the chemical potential of substance I in phase alpha times the differential of the number of moles of substance I in phase alpha is going to be less than 0. And remember, this is when we're not at material equilibrium. So this is an irreversible process. And this is still at constant temperature and pressure. So the chemical potential of substance I in phase beta times the differential of the number of moles of substance I in phase beta plus the chemical potential of substance I in phase delta times the differential of the number of moles of substance I in phase delta has got to be less than 0. So we want to substitute for that differential of the number of moles of substance I. So just like we did up there, saying they're equal by conservation of energy, notice we changed this to beta, now we got a minus sign here. So minus the chemical potential of substance I in phase beta is equal to the differential of the number of moles of substance I in phase delta plus the chemical potential of substance I in phase delta times the differential of the number of moles of substance I in phase delta is less than 0. So now we're going to factor out that differential there. So we have the differential of the number of moles of substance I in phase delta is going to be equal to the difference between the chemical potential I in phase delta and the chemical potential I in phase beta. And this is still an inequality, remember. It's less than 0 because we're not at equilibrium yet. Now, we're talking about the direction of we're going from, the solid dissolving in the liquid, so not the other way around. So this differential of the substance I, the number of moles of substance I in phase delta, this can't be negative. So instead, it's got to be this other difference, this negative. So we have the chemical potential of substance I in phase delta minus the chemical potential in phase I and substance I in phase beta. It's going to be less than 0. And this, if this is true, then we know we have an irreversible process. Now here's our chemical potential of substance I in phase delta, and this is our chemical potential of substance I in phase beta. So we're going to start out, we know that when we add the solid and it dissolves in the liquid, so the chemical potential of substance I in delta, that's the aqueous phase, is less than the chemical potential of substance I in the beta, that was the solid phase. So it starts out up here, and then as it dissolves it goes down, and then eventually it ends up down here. So what this is showing is that matter is flowing from the highest potential. I probably could have labeled that there. How about this? Mu I, something like that. Anyway, and then this would be just time, I guess. You want to add an axis to it or something like that. But anyway, so matter is going to flow from the higher potential to the lower potential until it's at equilibrium. So if the chemical potential of substance J in phase beta is greater than the chemical potential of the same substance in phase delta, then that substance J, given the chance, is going to flow from phase beta to phase delta. Now the temperature is related to average molecular kinetic energy. We talked about that before. So if the temperature in phase beta is equal to the temperature in phase delta, we'd say those phases are at thermal equilibrium. If the pressure in phase beta is equal to the pressure in phase delta, then we would say those phases are mechanical equilibrium. If the chemical potential J in substance J in phase beta is equal to the chemical potential of the same substance J in phase delta, then we would say those phases are in material equilibrium. Thermodynamic equilibrium means that the system is in all three types of equilibrium. I think we covered that in chapter 1 or 2, a long time ago. That's the end of chapter 8. Now we're beginning chapter 9, section 9. Chapter 4, section 9. We're going to talk about reaction equilibrium. So the subscript here is this coefficient here, A and B, this is going to be the amounts. So the A is the amount of substance A1, B is the amount of substance A2, etc. And then over here, these are the reactants on our side, the left side. And then on the right side we have the product. So we're going to have AM plus 1, etc. So as an example, let's say, what is this? 2 ethane plus 15 oxygen going to 12 carbon dioxide and 6 water. So our A1 is the C6H6. Lowercase a is 2. A2 is oxygen. and the B is 15. A3 is carbon dioxide, and the E is 12. And then A4 is the H2O, and F is 6. Now remember, our reactants and the products, they can be any phase. I would assume this is a gas phase reaction, but I don't know, maybe we could do it in the liquid, it doesn't matter. Now, moving everything to one side of the equation, just for mathematical purposes, we're going to end up 0 going to minus A, A1, minus B, A2, etc. for all the reactants, and then plus E, AM for the reactants, plus F, AM, plus 1 for the reactants, etc. So instead of using separate letters like A, B, C, D, we're going to use this nu. This is the same symbol for, it says frequency, actually I thought it was wave number. But anyway, so you might see the symbol before using a different meaning, so again, pay attention to context. So we'll just use a subscript. So nu1 will be the minus A, nu2 will be minus B, etc. Nu-M will be E, etc. Now the reason we did this then, so you'll notice all the reactants have negative numbers and all the products have positive numbers. So now we have 0 going to nu1, A1, nu2, A2, nu-M, AM, etc., etc. So we're going from 0 to the sum over I of the coefficient of I times the identity of substance I. So like I said already, nu I is going to be less than 0 for all the reactants, and nu I is going to be greater than 0 for the products. Now we have the change in the number of moles of I is proportional to nu I. Now remember, N is the number of moles, nu is the stoichiometric coefficient, and then in this case the alpha means proportional to. Now we're going to introduce a new letter of the alphabet, a Greek I guess. This is going to be xi, pronounced xi. This is going to be our proportionality constant. Remember, anytime you have a proportion, you can turn it into an equality just by adding a proportionality constant in there. So we're going to have the change in the number of moles of substance I is defined as Ni minus Ni naught. Remember, naught means the initial conditions. So final minus initial. So that's just the change. And it's also going to be equal to xi times nu of I. So this xi, this is going to be the extent of the reaction. So it kind of looks like an E anyway, so that makes sense. So the number of moles of substance I, the naught means the initial number of moles of substance I. And then Ni, this is just the at any time, the amount of I at any other time. Now nu I, it has no dimensions. It has no units. Now xi is going to be in moles, just like the change in the number of moles of substance I. So we're going to solve for xi, and we get xi is equal to the number of moles of substance I minus the initial number of moles of substance I divided by the stoichiometric coefficient, nu of I. So here's an example. Let's say we're going to go from nitrogen to hydrogen, or nitrogen and hydrogen to ammonia. So the stoichiometric coefficients, nu is just 1, 3, 2. But we want to know specific amounts. So we're going to say, okay, we'll start with 20 moles of nitrogen, 60 moles of hydrogen, and we'll end up with 40 moles of ammonia. Well then, delta N for N2 is going to be minus 20 moles, which is minus 1, that's our nu sub I is minus 1, times 20 moles. So the extent is 20 moles. For our diatomic hydrogen, we're reacting minus 60 moles. Our stoichiometric coefficient, nu I, is minus 3, and the extent is still positive 20 moles. The delta N for ammonia, we're going to end up with a positive 40 moles, so our nu is positive 2, and the extent is still 2. So the point is, the extent of the reaction is the same for everything. Here's another example. Here's what is that? Propane plus oxygen goes to carbon dioxide and water. So our nu is going to be minus 1, minus 5, positive 3, and 4. And, well, we don't have enough information to say the extent. So if we use 2.0 moles of O2 in the reaction, what is the extent of the reaction? Well, the change in the number of moles of O2 is equal to the number of moles of O2 minus the initial number of moles of O2. So that's going to be equal to the extent times the stoichiometric coefficient of O2. So solving for the extent, we get the number of moles of O2 minus the initial number of moles of O2 divided by the stoichiometric coefficient of O2. Now, we didn't explicitly say it, but we'll say we started with 0 moles, or no, we end up with 0 moles. We used them all up. We used up 2 moles divided by -5. Notice this is negative, this is negative. The negatives will cancel out, and you get the extent is 0.40 moles. So, part B, what is the extent of the reaction if we choose carbon dioxide as the basis for the calculations? Well, the extent better be the same, 0.4 moles. Okay, now let's talk about some simplifications. Let's say we have the sum over all the substances I and the sum over all the phases alpha. The chemical potential of substance I in phase alpha times the differential of the number of moles of substance I in phase alpha. So we could write that kind of distributing, moving around. The sum over all the phases I, or no, the sum over all the substances I, the chemical potential of the substance I in phase alpha is equal to the sum over all the phases alpha of the differential of the number of moles of substance I in phase alpha. So that's just going to be equal to the sum over all the substance I of the chemical potential of the substance I times the differential of the number of moles of substance I. That's going to be equal to 0. Since we're at equilibrium, so chemical potential I is going to be the same in every phase. We showed that before. For example, with the silver chloride, we had chemical potential of substance I in phase beta was equal to the chemical potential of substance I in phase delta. But that's only at equilibrium. And like I said, beta and delta are phases. So we have the sum over the substance I of the chemical potential I times the differential of the number of moles of substance I, and that's equal to 0. And this is at a material equilibrium in a closed system. Now remember, this chemical potential I for any phase that contains substance I. This is the differential of the change in the number of moles of substance I. So the differential of number of moles of substance I is, remember, is just equal to stoichiometric coefficient nu I times the differential of the extent for the chemical reaction. So the sum of the chemical potential I times the stoichiometric coefficient I times the differential of the extent is equal to 0. Now if we choose that the differential of the extent is equal to 1, then we could say that the sum over all the substance I times of the chemical potential of substance I times the stoichiometric coefficient of substance I is equal to 0. But this is at chemical reaction equilibrium, assuming pressure volume work only, closed system. But this is any process, like constant volume, constant temperature, whatever. So let's say we have constant temperature and constant pressure. Then the differential of the Gibbs free energy at constant temperature and pressure is equal to the sum over all the substances I of the chemical potential of substance I times the differential of the number of moles of substance I. And that's going to be equal to the sum of the chemical potential of substance I times the stoichiometric coefficient of substance I times the differential of the extent. So if we just divide, then we're going to get the differential of the Gibbs free energy with respect to the extent is going to be equal to the sum over the substance I of chemical stoichiometric coefficient of substance I times the chemical potential of substance I is equal to 0 at equilibrium. So as an example, here's a graph. This is the Gibbs free energy versus the extent of the reaction. So over on the left side we have pure reactants. Over on the right side we have pure products. So what this is saying, there's going to be some place where you're at equilibrium. This is the extent of the reaction at equilibrium. If you have more reactants, then the Gibbs free energy is going to go down until you're at the equilibrium. And if you have too much product, then you're going to go down this way. The extent's going to change until you're at the correct extent for equilibrium. So this xi equilibrium is the extent of the reaction at reaction equilibrium. When when the extent is greater than 0, the reaction goes to products. Okay. I think I worded that funny, because I think it should actually be if the extent is greater than the extent at equilibrium. Hold on a second. Let's see, when the extent is greater than 0, 0 is way over here. Something isn't right. Okay, I'm gonna have to look back at this part, figure it out later. Okay, skip that for now. So summary. So 1, the chemical potential of substance I, this is an I, not a 1, in phase beta is equal to the chemical potential of substance I in phase delta. That's our condition for phase equilibrium. And then 2, the sum over all the substances I of the stoichiometric coefficient of substance I times the chemical potential of substance I is equal to 0. That's our condition for reaction equilibrium. Now, if you notice though, 1 is actually a special case of 2. For example, let's say we go from A of A1 in phase beta to A and A1 in phase delta. And let's say that just A is equal to 1. The 1 is equal to A1 in beta and going to A1 in delta. So moving those to the same side, we get the minus the chemical potential of substance 1 in phase beta plus the chemical potential of substance 1 in phase delta, and that's equal to 0. So then we end up with the chemical potential of substance 1 in phase delta is equal to the chemical potential of substance 1 in phase beta. So therefore, like I said, equation 2 is a more general form of equation 1, or you could say that equation 1 is a special case of equation 2. Now let's say that for some reason substance J is not even in phase delta at all. Like let's say that J is just not soluble or something like that. Well, then we're going to get an inequality. For example, we'll say that the chemical potential of substance J in phase beta is less than or equal to the chemical potential of substance J in phase delta. So here's beta. I think this is supposed to be, should have an axis here. So this would be mu this way. This will be time this way. So over time, oh wait, so this one's backwards. Chemical potential delta here is lower than beta, but here it shows delta being greater than beta. So these two contradict. I'm gonna have to check on that and make sure one of these might be backwards. But what we said before is true. You're gonna go from the phase of the higher potential to the lower potential. In this diagram it shows beta to delta, but for some reason it shows delta higher than beta. Whoops. Okay, so here's the diagram. Here's a test tube. We got phase beta, phase delta, but we've got the same component in both. Component J is in beta, component J is in delta. When they reach equilibrium, you're going to have the chemical potential of substance J at beta is equal to the chemical potential of J in phase beta, delta. But that's the, like I said, at equilibrium. So if the chemical potential of substance J at beta is greater than the substance chemical potential of substance J in delta, then we're going to go from beta to delta. Yeah, see, I got this equality written backwards. That's all. There, now it's correct. Okay, if delta has no J in it, so if phase delta has no substance J in it, it'll still have a value for the chemical potential J though. So our chemical potential J of phase delta, remember it was defined as the chemical potential of the Gibbs free energy in phase delta with respect to the number of moles of substance J in phase delta, holding temperature, pressure, and all the other substances in the same phase constant. See handouts 15 and 19. That is the end of chapter 4.